So let's now talk about how to put backpropagation in the context of a computational graph. So basically, we are going up to the output doing a bunch of things like linear combinations, adding biases, passing through nonlinearities. So one general sort of forward path computation, I can write it as, okay, so let me make it, not even put a notation for this. So there's a computation going on. You're putting in some vector or tensor u. Let's just think of vectors. And you're getting out a vector v, and this is the computation flowing up the network. So let's look at what the chain rule tells me about how the derivatives propagate. So I have a loss function, and I'm trying to compute del L by del uj, say, right? Well, that's gonna be del L by del vi times del vi times del uj summed over all these i's. I'm not even going to say how many i's there are or how many j's there are, because I want to keep it fairly abstract for now. So v is closer to the output than u. We are sort of flowing up that way. So the only way uj can affect the loss function is through its through the variables vi's, and so that's what we have. And this del vi by del uj is sort of the ijth entry of a matrix that we call the Jacobian. Right, the Jacobian matrix, this is a notation for ijth entry of a matrix. So basically, what I really mean by it is the first row is del v1 by del u1, del v1 by del u2, etc. The second row is del v2 by del u1, del v2 by del u2, etc. Going that way. And I'm not specifying the dimensions of the matrix because I don't want any more notation than I really need. So now, again, let's do a shorthand for these derivatives like we started doing the last video. This derivative, let me call it uj bar on top, right? And this derivative, let me call it vi bar on top. So basically my generic notation is del L by del alpha is alpha with a bar on top. That's my generic notation for sort of the gradients that are propagating down. So if I look at this, let me change pen color quickly. This guy is the ijth entry of the Jacobian matrix. So what have we just written now? Let me rewrite it in red. uj bar is summation over I vi bar times jij. Well, this doesn't quite look like a matrix product, so I'm going to make it look like a matrix product by saying this is j transpose ji v bar I. So basically, in when I write down the entire vector of gradients, u bar on top will be j transpose v bar on top. So what is happening is that when I define this computation unit, I can effectively figure out what the Jacobian is going to be for that unit, and the Jacobian computation might well depend on the forward computation that I'm doing. We'll see a couple of examples, and we've actually seen the examples before. I'm now putting them in this abstract framework, and then I can sort of backpropagate these derivatives. So the input u is leading to a computation of v, and the derivative of the loss function with respect to v is leading to the derivative of the loss function with respect to u, through the transpose of the Jacobian matrix. Of course, this equation can often be simplified in specific instances, and we'll revisit some of the examples we did with this in mind. Okay, so let's see what happens when I go through a single a nonlinearity, and I'm going term by term through a nonlinearity, right? We have that happening for all these neurons, right? At any layer. If you look at a Jacobian, I mean, you have that, Vi is equal to psi of Ui. So del Vi by del Uj is psi prime of Ui for j equals I and 0 otherwise, right? Vi depends only on Ui and nothing else. So the Jacobian matrix is a diagonal matrix, and the ith diagonal entry is psi prime of Ui. So notice that the Jacobian actually depends on the current value of the Ui. The psi prime derivative is evaluated at the current value of Ui. So in principle, it can depend on what's happening on the forward pass. And so now we have that, what's the flow back here? Let me change pens. So suppose you have computed the derivative of the loss function with respect to V. What's the derivative of the loss function going to be with respect to U? So U bar is just J transpose V bar, but J transpose, it's a diagonal matrix. This is also equal to J transpose. So this is the diagonal matrix C prime Ui times V bar. So all that's happening is that the ith term is getting scaled by psi prime. So I can also write it in a simpler way as basically the vector of these psi primes. If I think of the psi primes as just a column vector, I can do a term by term product. This is called a Hadamard product with the gradient flowing back down, right? So basically the ith, just to be very, very clear, what's happening is that this is just saying that del L by del Ui, which is what I'm calling Ui bar, is equal to psi prime Ui times del L by del Vi. So seems like a lot of work to write it in this other fashion when you could have seen this immediately, but this tells you how basically we have a general computational framework in which all these examples fit. So now let's take the example of what happens from a output of a particular layer to the presynaptic outputs of the next layer, right? So again, I'm going to use the same notation. V is equal to W U plus B, right? This is what happens before I feed it into the nonlinearity, and you can see very easily that, and I'm going to use now this, I'm going to keep sort of simplifying notation. So this is the Jacobian of V with respect to U. So the ijth entry is del Vi by del Uj. So I might use this term for the Jacobian as well, or I could use this term for the Jacobian. But basically the bottom line is that the rows are corresponding to the V's and the columns correspond to the U's there. So that's what the Jacobian is, and it's pretty easy to see that this Jacobian is equal to exactly W. So we immediately get by the what we had was, so basically del V by del U is the Jacobian, it's equal to W. So as I flow down, U bar is going to be the Jacobian transpose times V bar, right? right? So those are the sort of gradients flowing down. Similarly, what about del V by del B, the biases? Well, that is just equal to the identity. You can see that del VI by del BI is 1 and del VI by del BA for the other guys is 0. So it's just the identity, which means that the gradient with respect to the biases is just equal to the incoming gradients with respect to V, right? Of course, what we are really interested in is adapting those weights, W's, and I'm going to leave it to you to show that the gradient with respect to W, and remember this is now a matrix of gradients, can be written as the inflowing, the gradients with respect to V coming in times U transpose. So that gives you the correct dimension. So for W, you can check that. So these are the. Let me change pen color. This is the desired gradient. So this is used for adaptation of the weight W, and this is used for adaptation of the biases B, right? These are the gradients that are used for that. Let's do one more example of the softmax, a softmax layer. Again, so I'm going to write softmax. I'm going to use the same generic notation. There's a vector U coming in, a vector V going out, and the softmax is that VI is equal to e to the UI divided by summation over j, e to the uj, and uv have the same dimension. And so my jij, which is the partial derivative of vi with respect to uj, and here's where I don't want to go through the details, and I'm just going to write down the answer, right? I mean, we have also derived it in at the end of the logistic regression handout. So this is going to be equal to basically minus vi times vj if I is not equal to j, and then vi times 1 minus vj for I equal to j. That's sort of a well, for I equal to j, this is just vi times 1 minus vi, but that's how I want to write it right now, because this becomes I can write this now as vi times delta ij minus vj, like I had done in the handout. That's why I wrote it that way. And so basically, now that you have the Jacobian, you can actually u bar is going to be j transpose v bar. And here the v is directly going into the loss function. This v business is just the y hats that we had before, right? So I know exactly how it hits the loss function. There's an L, y hat that it's affecting. So I can compute these derivatives. This is sort of just hitting the output directly, and then I'm propagating it down to what happens into the softmax. And how did the softmax things, how did these U's come about? Well, they're coming at the output of some of some neural layer. So basically, these three units are the main things you need. I mean, we did the softmax, we did just the linear weight field biases, and we did the nonlinearities. And just putting together the computational graph with these, you can do backpropagation and train a neural net to optimize, say, the cross entropy loss function. And that's sort of what these frameworks, software frameworks like TensorFlow and PyTorch enable you to do in a very elegant way.